Welcome back. In this lesson, we're tackling something that's no longer optional in modern networks, IPv6. We'll walk through how hosts actually get their IPv6 addresses today, and just as importantly, how IPv6 and IPv4 coexist in real deployments in 2026. By the end, you'll have a practical mental model of both addressing and transition, not just textbook theory. So here's our roadmap for the next few minutes. We'll start with SLAAC, the mechanism that lets IPv6 hosts configure themselves without a DHCP server, genuinely one of the most elegant pieces of the protocol. Then we'll look at EUI-64, the trick for turning a MAC address into an interface identifier. From there, we'll cover DHCPv6 for when you need stateful control. And finally, the transition strategies, dual stack, tunneling, and NAT64 that keep IPv4 and IPv6 working side by side. Before we dive into SLAAC specifically, let's zoom out and see the full menu. IPv6 actually gives us 4 ways to hand an address to a host. At one end, there's manual configuration, what we still use for servers and routers where predictability matters. Then SLAAC, where the host figures things out on its own. DHCPv6 brings back the stateful, centrally managed model we know from IPv4. And in modern networks, we often combine the last two. SLAAC for the address, DHCP for things like DNS servers. So let's unpack that magic. SLAAC happens in 4 steps. First, the host builds itself a link local address using the FE80 prefix and an interface ID derived from its MAC, that's the EUI-64 trick, or a randomized value for privacy. Second, it runs duplicate address detection, basically shouting, "Is anyone already using this?" before claiming it. Third, it sends a router solicitation to the All Routers multicast group, asking what prefix lives on this link. And finally, it glues the prefix from the router advertisement onto its interface ID, and just like that, it has a globally routable address. No DHCP server in sight. Now let's actually walk through that EUI-64 trick I mentioned. We start with a standard 48-bit MAC address, and we split it right down the middle, wedging the hex value FFFE into the gap. That's our padding to stretch it out to 64 bits. Then comes the slightly weird part. We flip the 7th bit of the first octet, the universal local bit. So 00 becomes 02, and once we regroup everything into IPv6 4 hex-digit blocks, our MAC has become the interface ID R21B, 12FF, ABBCC. But here's the catch with EUI-64, that interface ID is literally your hardware address, broadcast to every network you touch. Coffee shop, home, office, same trailing bits every time. Advertisers and trackers love that. So RFC 4941 introduced privacy extensions. Instead of deriving the interface ID from your Mac, the OS generates a random 64-bit value and rotates it, typically daily. Windows, macOS, iOS, and Android all do this by default now. On Linux, you flip it on with the SysAdmin stomp temp pattern set to 2. Now, alongside SLAAC, IPv6 also has DHCPv6, and a fair question is, why both? They actually solve different problems. SLAAC is stateless. The router announces a prefix, the host picks its own interface ID, and nobody keeps records. DHCPv6 is stateful. A server hands out full addresses and logs every lease. SLAAC also needs an RDNSS option in the router advertisement to convey DNS, while DHCPv6 carries that natively. The rule of thumb, SLAAC fits home and simple networks. DHCPv6 wins where you need auditing, control, and compliance. Think enterprise. Of course, getting an IPv6 address is only half the story. We still live in a world full of IPv4, so the two have to coexist. There are 3 strategies we reach for, and the right pick depends on what you actually control. Dual stack is the default today. Every device runs IPv4 and IPv6 side by side. Applications choose and nothing gets translated. Clean, but you're maintaining 2 parallel plans. Tunneling wraps IPv6 inside IPv4 packets using something like 6N4 or GRE. Perfect when you have IPv6 islands stranded across an IPv4 only carrier. And translation, typically NAT64 with DNS64, lets an IPv6 only client still reach legacy IPv4 servers, common in mobile carriers and modern data centers, though it does break end-to-end and trips up any protocol that embeds IPs in the payload. Let's zoom in on dual stack because it really is the modern default. Every device, your laptop, the router, the server out on the internet holds two addresses at once, an IPv4 like 168.1.10 and an IPv6 like 2001 DB8.1 to a. When you type example.com, DNS hands back both an A record and an A record, and the browser uses what's called happy eyeballs from RFC 8305. Try IPv6 first, and if it doesn't answer within roughly 200 milliseconds, quietly fall back to IPv4. You never see the race, you just see the page load. Dual stack works beautifully when both sides speak IPv6, but what about modern mobile carriers that have gone IPv6 only? They reach the legacy IPv4 internet using a clever pair, DNS64 and NAT64. Here's the flow. Your phone asks for example.com, and if only an IPv4 record exists, DNS64 fabricates a synthetic AI address by embedding that IPv4 inside the well-known prefix 64.f9b. The phone happily sends an IPv6 packet to that address, which routes to the NAT64 gateway. NAT64 then strips out the embedded IPv4, forwards a normal IPv4 packet to the real server, and wraps the reply back into IPv6 on the way home. The phone never knows IPv4 was involved. Let's get our hands on the actual configuration. On a Cisco router, the very first step is enabling IPv6 routing globally with IPv6 unicast routing. Without that, the router will forward IPv4 but quietly ignore IPv6. Then on the interface itself, we layer both protocols, a traditional IPv4 address, an IPv6 global address, and IPv6 enabled to guarantee a link local. A quick show IPv6 interface brief confirms both the link local starting with FE80 and our global 2001 DB8 address are live, and that's dual stack running on a single wire. With the configuration piece in place, let's pull the whole lesson together. 5 ideas to carry forward. SLAAC lets a host build its own address from a router advertised prefix. EUI-64 is the deterministic way to derive that interface ID from a MAC. Privacy extensions, then randomize it so we're not trackable. DHCPv6 steps in when we need stateful control, often alongside SLAAC. And out in the real world, dual stack is the norm, with tunneling and NAT64 filling the gaps between V4 and V8. And here's your cheat sheet. Keep this one handy. Notice how it maps the whole journey. SLAAC and the RRARS exchange at the top, then how interface IDs get built with EUI-64 or randomized for privacy, DID making sure no one else has claimed the address, and DHCPv6 layered in when we need more control. The bottom rows are the coexistence story. Dual stack as the default, happy eyeballs smoothing the user experience, and tunneling for when native IPv6 just isn't there yet. And that brings us to the end of Lesson 24. Up next is the Stage 3 capstone, where we'll pull everything together, IPv4 subnetting, VLSM, and now IPv6, into a real design exercise. That's where the theory becomes muscle memory. Take a breath, review the cheat sheet if you need to, and I'll see you in Lesson 25.